Hello, everyone. Welcome back to Temporal Reading Group Summer Edition. Hope you are all having a good day and uh, best of luck with the review period. Um, so we are very excited um, to have Zijie Huang today, who will be presenting her PhD thesis, right, on neural dynamics for science, the symbiosis of deep graph learning and differential equations. Um, and I will do a little bit of speaker intro first. Zijie Huang is a research scientist at Google DeepMind, building Gemini. Her research interest lies in generative AI, AI for science in general, with a special focus on LLMs, dynamical system modeling, knowledge graph reasoning, and diffusion models. She obtained her PhD in computer science from UCLA, where she was co-supervised by Prof. Yizhou Sun and Prof. Wei Wang. Her research was supported by the Amazon PhD Fellowship, and she was selected as EECS Rising Star in 2023. So I will hand the mic to you.
Okay, yeah, thanks, Andy, for the nice introduction, and happy to give my talk here to everyone, and welcome to my talk today. Today I'm going to present my work regarding neurodynamics for science, the symbiosis of deep graph learning, and differential equations. So feel free to interrupt me for any clarification questions during the talk, and for more questions during the Q&A session. Okay, so to begin with, our world consists of many complex structures in dynamics underlying across different domains. For example, the COVID-19 spread in the past few years can be viewed as a combination of these two, where you can see each state has daily confirmed death case over time. In the meanwhile, there are population flow among different states, across different states, transmitting disease from one to another. As a consequence, the US government has spent huge efforts in controlling the spread of disease. So they have spent $16 trillion on this compared to the economic crisis happened after 911. So such problems can be formulated as a dynamical graph, where a set of objects interact with each other over time, forming trajectories. There are a lot of examples across various scientific domains, such as fluid dynamics in physical simulations, where you can view each particle as a node and their interactions is basically bounded by the Euclidean distance of different particles, and brain network in biomedical engineering, where you can imagine each region of your brain as a node emitting signals along the time, and a lot more in molecular dynamics, sports analysis, where you can view each angle of a person as a node and the skeleton connecting them as edges. So the essential problem we care about in dynamical system modeling is a knowing problem, saying that given the historical trajectories in the past and potentially the interaction graph among different objects, can we make accurate predictions in the future, such as prediction of the 5 balls connected by springs? So dynamical system modeling can have huge impacts to our daily life. Back to year 2008, I experienced Wenchuan earthquake in my hometown China, where I see a lot of land collapse, etc. I hope there were some early warning systems so that people can run away and survive. On the other side, dynamical system modeling can also facilitate scientific discoveries. So for today, 9 out of 10 most powerful supercomputers in the world are used for simulations. So if we can have a surrogate neural simulators that approximate the simulation process using neural network, we can save a lot of computational resources. So dynamical system modeling can also facilitate decision making for scientific discovery, such as understanding the causal relationships towards different policies, how they affect the spread of COVID-19, or even make healthcare interventions towards which characteristics of the patients can be the decision maker towards the treatment. There are two main branches for dynamical system modeling. The first branch is basically logic-driven ordinary differential equations, such as Newton's law of motion, which describes the continuous evolutions of variables over time. So in the context of multi-agent dynamical system, where we have objects interact with each other, the general ODE form can be summarized as follows. The state derivatives of node I, which is determined by the influence from itself as well as the influence from its neighbors. Taking examples of epidemic spread, we can see that a person's infectious rate at the derivatives of xi can be negatively proportional to its current health condition xi as well as infections from its connected neighbors. So given the initial states of an ordinary differential equation as well as the ODE function g, we can call any black box ODE solver to such as Euler's methods to compute state trajectories over time. The choice of different ODE solvers offers trade-off between precision and efficiency. So here I show you a diagram comparison of Euler's solver and adaptive solver. So Euler's solver is usually relatively fast due to its rough approximation. An adaptive solver can adaptively adjust the step size over time, offers more precise modeling, but it's usually slower. So logic-driven ODE has several advantages, including they offer interpretability because the ODE function g can be directly written out in symbolic form, and it can model continuous system dynamics over time and offers analytic solutions. However, the ODE function g usually are handcrafted from domain experts, which are expensive to obtain and sometimes are even unknown. On the other hand, I think we are all familiar with data-driven approach, which highlighted by graph neural networks. So basically, we can also learn system dynamics automatically from data. So among them, graph neural networks are neural networks that operate on graph structured data and are very suitable for modeling multi-agent dynamical system. It's basically updating each node's embedding vector HV based on its representation from historical timestamp t-1, as well as representation vectors from its own neighbors. So for GNN, GNN basically make predictions in a discrete manner, saying that given the current state at timestamp t, we roll out the trajectories for t+1, t+2, etc., and then trying to make predictions over time. So here is just a diagram from researchers in Stanford and Google DeepMind develop these neural simulators using graph neural network. So they basically serve as a fixed step transition function, which reveals how system changes from t to t+1 compared to ordinary differential equations. So data-driven GNNs also offers many good advantages. Because they are learned from data, they are more easily to generalize across different data samples, and they are scalable by utilizing the training algorithm of neural network, and they offer flexibility because the function is basically learned from data. But the major drawback is that they learn systems in a discretized ways compared to ordinary differential equations, which brings several issues. So the first thing is that such discrete manners cannot handle data irregularity. So here, for example, I show the trajectories of three body problems. And for each of these objects' trajectories, they can happen at irregular time steps, like along the temporal aspects and also along the spatial aspects at a specific time t. It may be possible that only partial of the objects are observed. For example, among all of the 7 different time steps, only at timestamp 5 we can observe 2 objects, and at remaining time step we can only observe mostly 1 object. So recall again the function we introduced in the previous slides regarding GNN. The updates function will require the states of node itself as well as all of its connected neighbors. So if some of the neighbors' information is missing at a specific time, we can no longer do the aggregation over time. And also the discretization also struggle for modeling usually long-term dynamics because you can imagine the rollout error will accumulate over time. And in comparison with ordinary differential equation, you can think about discrete GN as a very rough solver for ODE. Basically, the step size compared to ODE solvers is very, very large. So you can imagine the error accumulation when we do only a t plus 1 step will cause very huge error. In contrast to ODE solver, such small step may already be integrated or updated through many small delta t. So that motivates us to think about if there's any bridge in between that combines these two words together. So my solution is like develop a series of work called graph ODEs, which basically combines graph neural networks with ordinary differential equations. So to bridge these two worlds, I basically extends discrete GN dynamics to continuous neural dynamics. So this is got inspiration from neural ODE for sequence data. To model the interactions among different objects, we parameterize the ODE function using a graph neural network and learn system dynamics in the latent space using representation learning. So specifically, we have proposed our first graph ODE framework in the year of 2020. It is a generative model following the architecture of encoder ODE processor, encoder processor decoder architecture. So basically, the key takeaway is that we want to model system dynamics in the latent space with representation learning. So think about again the ODE function I showed in the previous slides. Traditional logic-driven ODE, they basically model concrete physical variables. For example, XIT can be the positions, locations of some balls, and G is basically some predefined ODE functions handcrafted by domain experts. So in these frameworks, we replace all state variables as high-dimensional vectors, the IT, and the G becomes a learnable neural network, G theta. So as I mentioned, it follows the encoder processor decoder architecture as usual. So as an initial step, we have the initial state estimation, Zi0, through an encoder network, which takes the historical trajectories and potentially the interaction graph as input. And then we can call any black box ODE solver that infers the IT at arbitrary time through integral. And finally, since we model system dynamics in the latent space, we can decode it back to the physical scene that we want to make prediction of. So we have a simple decoder to translate from ZIT to our predicted variable YT. So we basically train this framework using like the alpha loss, which basically consists of two terms. The first term is the standard reconstruction loss, which basically minimizes the prediction value towards a ground truth value. And the second term is a regularization term happened in the initial states, which basically will regularize how the distributions of the inferred latent states scattered around. So you can basically assuming that it will limit how different starting points of trajectories will scatter around the space. So it's kind of making things more similar to each other. So here are just two real-world examples where we can encounter irregular observations where discrete GN may fail to solve such problem very naturally, although there's also some techniques to apply. For example, in climate change, the irregularity that I'm referring to is more happening on the spatial domain because the sensor that we placed in different regions, their updating frequency can be very different. So like there's multi-scale problems in the temporal domain. And for traffic network in Los Angeles, for example, it's more like in the it's more like if you want to search for some certain cars, something like this, it's not likely you can get connected to all sensors at all time because they are moving around very rapidly. So to go into a little bit details how these
Just a quick
frameworks.
question.
Oh
Sorry.
yeah, please go
Just a quick
ahead.
question. So here you assume the graph, which is kind of the relations are given, right? So the GNN input graph is always fixed over time.
Yeah, that's a very good question. So this is the first paper that we start graph ODE. So we make the simplest assumption. The graph structure itself is given and fixed. Only the trajectories evolves over time, but we have many follow-up work which consider latent graph structure, and also the graph structure itself evolves as well.
Okay, sounds good. Thanks.
Yeah. Okay, so just a little bit more details how the current frameworks learn from irregular observations. The thing is that we have a encoder which trying to consist of a graph transform and temporal encoding, which are able to infer the initial states of the ODE function from irregular observations, and also regarding the training labels, because consider the output of any ODE function. As I mentioned, we can output any desired state, ZIT, where T can be any continuous number. So labels observed at arbitrary time can be used as supervision signals. In contrast to discrete genes, you need all labels at a specific time t. So you can look into more details into our paper, so I will omit those details for now. Towards the evaluation, we have tried on 3 simulated dataset as well as 1 real-world dataset, real-world dataset which are human motion that I described before, and 5 body spring system, 5 body charge particle system. So the task setting is basically towards interpolation and extrapolation with irregular observations, where the differences between interpolation and extrapolation is that whether we want to make predictions of data points at within the same time range or based on the observations in the past and make predictions in the future. So we have seen do the comparison of many existing baselines at that time, and we're able to see that compare against both continuous baselines, where ODE based and many discrete GN based approach across different observation ratio, which is how many data we want to mask out through the historical observations. We can see there are consistent gains across different observation ratios and also across baselines. And we also are able to see larger improvements, especially in the extrapolation task, which is usually more challenging compared to interpolation task. So yeah, so here's just some animations that I made. So just a brief summary here. We basically provided a principled way for modeling continuous system dynamics with learnable neural networks. And through experiment results, we found it's very suitable for modeling long-term predictions and are very efficient for learning from irregular observations. So far I have talked about our work regarding bridging neural networks with ordinary differential equations, which called graph ODE can solve continuity in dynamical system modeling. But there are still a lot of different challenges exists, which basically arise from the modeling part, data part, application part. For example, in modeling part, we may care about how the model can generalize across domains and how can we do accelerations because some ODE solver can be relatively slow, as I mentioned before. And from the data side, we can think about whether we can inject various data-inspired inductive bias related to physics-informed neural network, etc. And for applications, we can think about whether we can extending from simple predictions to intervention so that we can combine, for example, causal reasoning to support decision makers, such as COVID-19 policies. And we also have explored how to use those continuous approach to predict neural network training dynamics, especially for the training expense is relatively high, so we can directly through the loss curve to see if we want to continue this run. So just some efforts that have happened after like this paper that I introduced before. So here I summarize some of our like achievements so far. So we have different branches that we look into and have published papers in these domains. And overall, this graph ODE series work has been supported by Amazon PhD Fellowship. And we also have a new NSF medium. Actually, it's not new for this year, but it's basically a new NSF award. So solely consists of all graph ODE series work that I listed here. And we also have a new KDD tutorial this year. But sadly, I cannot attend in person, but my collaborators will present in person there. So for today's talk, I think I will introduce two more work, which from the model generalization and also data-inspired inductive bias. And finally, briefly mention one work about from prediction to intervention. So I will keep those work mostly highlighted and omit some more details you can look into the papers afterwards. So let's start from the first part towards more generalizable graph ODEs. So the basic motivation is that in many real-world scenarios, we might observe data that are generated from multiple systems which only differ in their environments. For example, here I show you some water movements in a container, but containers have different shapes of wraps. So you can imagine when the water particles collide with the wraps, their trajectories or directions will change automatically. And also multiple movements with different temperatures because they will affect the speed or the internal energy of them. So their moving trajectories can also be very different. So a very simple solution towards solving those systems that I show here is that we have multiple one-to-one models, which are called per environment models. So of course, it's very expensive to train and fail to capture the commodities across environments, offering poor results for data sparse systems. So for example, at a specific container shape or temperature, I only have limited data points. Such per environment models may not be good enough due to data scarcity. So of course, an alternative approach is to deploy one-to-all model, which makes up training examples across environments. Basically, you can imagine we can simply mix up training trajectories from different temperatures or different container shapes, and then train a one-to-all model. Hopefully, it can solve them all. But those one-to-all model may fail to generalize well due to lack of exogenous factors modeling, because if we simply merge all data together and mask the model to train, the model may not directly explicitly tell if those data are from different environments or not. So in this way, in this work, we try to build a one-to-all model that assumes that the dynamics across environments are governed by common physical laws, but there are some exogenous factors such as temperatures, container shapes, which will affect the dynamics. So again, in this simplest setting, we assume the environment variable will not change over time, but we have follow-up work will assume the changes of environments as well. So the basic idea we have here is recall again the ODE function I showed previously, which is the IT equals to initial state plus the integral of the ODE function. So here, what we made a simple change is that the ODE function G we assume is shared across different environments. But for each environment, we will have a environmental vector, which is unique, nerd from the environment from the data, and we plug in such vectors into the ODE function to account for their differences. So this can be understood from our previous toys examples in disease spread. So recall I talk about the infectious rate of a person is determined by both itself and its affections from neighbors. So here we can see maybe the coefficients B and R here we assume are the same for all environments which are existing one-to-all model. But here, in our approach, we just assume the general function form are the same, which compromise of these two parts. But the coefficients, for example, the B and R, can be individually set for each environment. So that's a like a comparison towards existing approach. So then the question lies in how can we learn such environmental vectors? One solution is that we can have a learnable embedding table of environments, but this only works for transductive setting, right? Because when you have a new environment in the testing stage, you cannot have its value looked up in the existing learnable table. So we want to learn environmental vectors automatically from observational data, which can be easily applied to those unseen environments. So we can do in the inductive setting. So the way we do that is basically we have a environmental encoder which also takes the node trajectory inputs as well as its potential interactions, which output a vector called UE. And this UE we will plug in the ODE function that I showed before, basically concatenation with each node state vector, and then we will plug in this new vector back to our original node ODE functions and then do the evolution over time. So it's very simple idea. But there are two main challenges for learning those environmental vector UE, which I identified. The first thing is called time invariance, because here we assume the environmental vector stays static over time, and we learn those vectors basically from the observational trajectories. So we would expect that when we learn from different truncation windows, we hope the resulting UE can be similar. So consider we have two environments E and E prime. So the basic idea is that we want to enforce the environment vector output from this blue and orange table to be similar to each other, but orange and green table to be apart from each other because they are from different environments. So we achieve this through contrastive learning loss. So of course, it's not 100% guarantee the blue one will generate the same one as orange, but we found this additional loss is very useful for help us learning the whole procedure. And another thing is called the orthogonality, because recall in the LGOD paper I introduced the initial state vector Zi0, which is also learned from historical trajectories. So basically, the environmental encoder and the initial state encoder takes the same input, but their output purposes are totally different. So we utilize mature information minimalization to try to disentangle the output symmetrical milling of these two encoders. So that's basically gives us now the overall picture of this GGODE framework. We'll compared to the LGOD framework, we basically have one additional environmental encoder plus two loss. So the final loss is a weighted combination with the original alpha loss plus a contrastive learning loss and the mature information minimalization loss. And here's some experiment results. So we have seen like improvements towards both transductive setting and the inductive setting. And there's more gain in the inductive setting, which is even more challenging. And there are some like animations from our model towards predictions and comparison to the ground truth. So there are some follow-up work I just show here. So we have follow-up work trying to see if the environment is also co-involving with those individual trajectories, and also how we can generalize across different system instead of environments such as a mixture of water, sands, etc. And also our newest ICML spotlight paper trying to study the generalization through explicitly modeling the causal relationship between coupled objects. So feel free to take a look. And then we can briefly talk about the second part, which is injecting data inspired inductive bias. So I'd like to start with some two examples. So previously I showed you that the co-evolution, the spread of COVID-19 basically can be viewed as a co-evolution of both nodes and ages, because the population flow among different states will change daily. So that's go back to Andy's previous question. So in this problem setting, we probably want to model the joint evolution of both nodes and age. And also in one of our collaboration paper with material science people, we have studied different material types where there exhibits different orders of dynamics. For example, this is a figure from our Material Horizons paper. So on the above, I show you the interactions of radial two-body interactions, which are basically capture some long-range Coulombic interactions, etc. But on the other side, it's another material which basically comprise of more complex angular and radial interactions. So it's more like angular three-body interactions, where the interactions is not solely dependent on the distance between its neighbors, but also the angle between two neighbors. So those different behavior basically implies that for some dynamical system, we probably want to also model its dynamics in different uh, orders. So we have some paper trying to study second order graph ODEs or in the temporal domain, or even spatial higher order dynamics in the context of multi-scale dynamical system modeling.
Just a, yeah.
Uh,
If you don't mind, just a quick question on the previous section on the generalization.
oh, sure.
So yeah, so I find your approach very interesting. So basically, the environment vector that you learn is basically the same as the initial node state vector, except you use two losses to force it to learn individual environment dynamics, right?
Right, the architecture of the environmental encoder and initial state encoder are pretty much similar, but there are two different sets of like neural networks, so they have different weights.
And here by inductive, do you mean that you have a new environment encoder that you don't need to learn, you just apply, or do you need to train a separate environment encoder for the inductive environment?
Yeah, that's a very good question. So go back to these slides. When I see inductive and transductive, is that, for example, if you consider you do not know this UE from observed trajectories, another way is that like doing KG, you can have a huge embedding table for environments, but that embedding table will only have values for temperatures, for example, that you have seen during training. So during testing, if you have a
Mhm.
new temperature, the embedding cannot be retrieved. So here, in the inductive setting, our approach, once the training is finished, the environmental encoder is already been trained. So during testing time, if you have a new temperature data comes in, you can just plug in its observed trajectories. So the environmental encoder can just output a different vector based on the input trajectories. So no need to retrain it, but it's kind of the parameters of the encoder is shared across different training testing examples, but the output will be dependent on the input trajectories, which are naturally different.
So basically, you are doing simply just forward pass at inductive case.
Yes, we do not try anything so complicated, but in our recent ICML paper, I think it's conducted by one of my intern. So there's
Mhm.
some more complicated like studies regarding how we handle environments and something like this. But as this is kind of the our first try to see if we can study generalization, and we found this simple
Right.
approach actually already works well on our simple systems.
Yeah, yeah. So, yeah. So yeah. So I believe it can work. So actually, I've had some paper that we tested out that you can also do just forward pass for like unseen temporal graph, and it also works out of the gate. So my question is mostly about. So does it mean that? So I know this is a tricky question because the definition is not clear. So does it mean that you have a foundation model kind of? So is it kind of like equivalent, like in your mind, or do you feel like a foundation model for the dynamical system that you want to tackle would need something else as well? Or do you feel like you can just, if you know it's a similar environment, you can just feed in some observations and it would generate the environment encoder, it can just adapt to it? Or do you feel like there should be something more?
Yeah, that's a very good question. So I think it depends on the thing I listed here. So I think if those systems, for example, they are only differentiated in environments. So you can imagine here the two examples I show, the way I generated those systems basically is by just changing the ODE functions part parameters. For example, just changing the scalar of the variable controlling the temperature or some barrier conditions, but the general ODE function form remains the same. So that's what I call generalization across environments. I think for those cases, it may be okay. We just learn some environmental variables from data. But a more complex setting is more like we want to do generalization across system. So like water and sand, because they are different materials and their ODE interaction function can be so different because one of them is solid, one of them is liquid, something like this. So in this case, I don't think such simple approach will work because we have done something on our side as well at that time. If we simply use the similar approach, trying to study the mixed movement of water and sand doesn't work that well. So I think for such more complex or high-level generalization, it may necessitate the usage of a foundational model that may already see a lot of different data, but still it has some basic capability to understand the underlying physics. So they may not be simply treated in this way.
Okay. Yeah. Thanks for the answer. That's super interesting. Thanks.
Yeah, thanks for the question. Okay, so let's go back to data-inspired inductive bias. So besides high-order dynamics, so we also know a lot of work in the lines of physics-informed neural networks. So they basically apply many physical constraints to different systems, such as the energy conservation law, which describes the summation of potential energy and kinetic energy should remain the same if there's no external force or some interactions with the environment. So I'm here trying to introduce one of our work in injecting physical constraints. The paper is called Tango, which won the Best Paper Award at DLD workshop at NeurOps 23 and accepted at NeurOps 24. So just to start with, the basic motivation for our paper is that we want to achieve high precision modeling of physics-informed neural networks. The thing is that purely data-driven neural networks such as graph ODEs can violate some physical properties such as energy conservation law, leading to no precision predictions. For example, here I show you a system, a spring system which do not have any frictions with the floor. So the ground truth energy should remain as a blue line, which is unchanged. But what we have found is that if we directly apply the previous LGOD to make predictions, although the prediction error may seem like within a reasonable range, but if we check the system energy, which is a green line, it will not follow the basic physical laws. So there are some existing physics-informed neural networks, such as Hamiltonian neural network, which strictly enforce energy conservation. However, but not all systems are strictly energy conservative. So this is only one type of physical prior that can help to achieve high precision modeling, but only to a specific group of systems. So we want to see if there's some more general way that we can achieve high precision modeling across different system groups. So yeah, here is just two more examples showing cases where the spring system can be non-conservative. For example, if we have frictions, mu here with the floor, or if we have external forces, the energy curve will look like those two things. So yeah, again, we want to achieve general high precision modeling for various systems. We get our exploration from this figure in the beginning. So for most dynamical systems under classical mechanics, if they are energy conservative, they are also time reversible. But there are also some systems that are time reversible but not energy conservative, meaning that time reversible is a larger concept than energy conservation law. So the time reversal symmetry is basically saying that if, for example, here I have a pendulum, if I swing it from point A to point B, and then at point B, I just revert its like direction and assume there's no frictions, etc., then it will naturally swing back to A following the same trajectories. So more mathematically saying is that, let's say I have a trajectory starting at here. if I do the following 4 operations, phi t, which is evolution over continuous t, reverse, which is reverse the state at the endpoint, phi t, which is evolve back again phi t, and reverse, which is finally collapse back. Then I will go back to what I am at the initial states. So the z will not change at all. So what we have done is also very intuitive thing and very simple. So again, we model we are trying to force the time reversal symmetry for such systems. And the way we're trying to do that is that we're trying to minimize the differences of the forward and backward paths in the latent space. So basically, we add the ODE to generate the trajectories in the forward step, and then we apply the reverse way and then phi t. So we can have 2 trajectories called forward trajectories and reverse trajectories, where they basically share the same returning points. And then we can simply have a reversal loss, which is basically the minimization of the equilibrium distance from all connected data points along these 2 trajectories. And then we do the weighted combination of these 2 through a coefficient called alpha. So here I want to highlight that the way we enforce time reversal symmetry is very intuitive through a loss function. And this is only a soft constraint because the second term reverse cannot always be 0, meaning that we are not strictly force time reversal symmetry. There are some benefits for that because later on when we apply this approach to many real-world systems, it's hard to see if they strictly follow or just partially follow. So we can always control the alpha coefficient to apply to different systems that we want. But this is just our starting point. We want to utilize time reversal symmetry to cover broader dynamical system. What we found very interesting is that in practice, we observe this approach could in general improve modeling accuracy on various systems, even regardless of their physical properties. So we want to understand why. So here I show you what we have found, which is the numerical benefits of our model Tangle. So here, if we let delta t to denote the integration step size of an ODE solver and the big T to be the prediction length, then we found that the prediction loss, which is proportional to t the power of 3 and delta t power of 2, and the time reversal loss is like this. So what we can get indicated from this theorem is that if we look at the relationship of these 2 laws regarding delta t, which is the step size of ODE integral, the reversal loss is minimizing higher order Taylor expansion terms, such as derivatives of accelerations, which force the model to focus on more fine-grained physical properties. Because delta t squared is basically minimizing something like if our input is location, so delta t is just a velocity, and delta t squared is acceleration. But here the reverse loss is minimized delta t to the power of 4. So it's more like the derivatives of acceleration, which is called jerk. So there are some more fine-grained physical properties the second loss is forcing the model to minimize. And we can also look at the relationship towards the big T, which is the prediction horizon. So we can see that the reversal loss is more sensitive to the total sequence length. Thus, it kind of provides more regularization for long context prediction, meaning that it will have more penalty to errors, especially happened in the long horizon. So together with those 2 observations, we see that Tango is able to, in general, help learn more fine-grained and non-contact system dynamics, regardless of system physical properties. So the proposed TRS loss, which is time reversal symmetry loss, can be viewed as in 2 different domains. So even though we're starting from injecting physical prior with the inspiration from time reversal symmetry itself, we have this theorem saying that it can help us reducing error accumulation over integration steps. So that's basically the interest points for this work. We do the evaluation on the 3 different spring system, which is combination of different physical properties, whether conservative, reversible, etc. We also consider experiments on a challenging triple pendulum system, which is highly sensitive and chaotic. Sensitive means that here I show you if I do a simple interpolation on its initial states, showing on the dotted line, the trajectories will be totally different, even if I do not change anything else, just slightly interpolation towards its initial states. So this makes this pendulum system a little bit more complex than the spring systems we showed before. And we are able to see consistency. I should update this table. We have a more concrete table in our final paper. So we can see our approach is able to achieve general gain across different compared methods, even if it's purely data-driven, which is latent ODE, or it's physics-informed. But those physics-informed, like Hamiltonian neural network, is only for conservative systems, and existing approach may only target at other physical properties, so they may not generalize well for all of the different systems that we are showing here. And again, there's some like trajectories visualizations from our model and some like compared baselines. So yeah, that's basically the second part. We talk about data-inspired inductive bias. So there are many different bias. We also talk about like higher order dynamics, co-evolution of nodes and age, etc. So feel free to check some of our work later on. And finally, I want to quickly wrap up the third part, which is graph ODE for causal decision making, which we extend from simple prediction to support decision making, trying to understand if there's some covariance or hidden factors that affect the overall trajectories. So I want to start a little bit the background of why we want causal inference. So consider if you want to study whether vaccines can help to improve health condition, we can simply connect a set of data points and then trying to see if there's a positive correlation. But if we just simply treat all data points as the same, which is denoted as those black points, we will find a negative correlation, saying that indicating that vaccines actually can hurt health condition. So why is that? This is because those data points are connected from different age groups. So if we split those data colored by their age group, for each group, we are able to detect a positive correlation. So that is what we call covariance in this case. So we need to understand if there's some hidden covariance, such as age in the case, that will affect my input and output. So causal inference in dynamical systems has two major challenges basically brought by the long IID data. So again, if I think about multi-agent dynamical systems, I can extract individual causal graph that are highlighted here, which is a triangle graph for each node independently. But since these nodes are interacting with each other, there are two additional types of covariance or causal relationships existing. The first one is called neighborhood confounders, which basically saying that if your family members are in poor health, you may be more likely to receive a vaccine. And the second one is called imbalanced interference, which basically says that if a unit's friends receive vaccines, a unit may be more immune to virus. So these are some like concept related to causal inference. So I just provided some simple examples to better understand that. So what we did is called a treatment-induced graph ODE, meaning that we can utilize this graph ODE framework to model the continuous treatment effects so that we can answer questions like, what if stay-at-home policy is applied 1 month earlier? And we also have a treatment fusing stage so that we can have a answer questions such as, what if stay at home and get vaccine policies are applied simultaneously? So the key things that we trying to overcome the imbalanced treatment, such as the age group thing we mentioned in the very beginning, is using adversarial learning to achieve unbiased estimation. So we applied those approach to COVID-19 policy analysis and find that some interesting findings, such as which policy we should remove first and the relative type of the policies, how they will affect each other. So those are just some very rough introductions to this line of work. If you are interested, feel free to look into more in the future. Yeah, and I think that may be the end of that talk. I have some future directions, but that's basically last year when I am on academia job market. Uh, yeah, I think maybe given the time limits, let's directly move to the QA session. And thanks again, everyone, for attending this talk.
Yeah, thanks for the super interesting talk. Definitely learned a lot from the talk. And for the audience, feel free to ask any questions. I always have some questions to ask, but feel free to type your question in the chat and I can ask, or you can just unmute yourself to ask. So feel free. Um, so so thanks for so I can start maybe. Thanks for going over your work. It's actually highly structured in the sense that it's well organized into the systems that you mentioned, and it's super nice. Um, so I was thinking one thing that's quite interesting. So like the time reversal loss you were talking about, I
Mhm,
wonder if that can be applied to temporal graphs because, and I think maybe I'm not sure if you have think about it like Julia, but I feel like everything we do nowadays is just rolling over the trajectory and do forward pass in the sense that we
mhm,
move forward in time.
mhm,
But maybe we should be forcing the model to know how do we get back to the initial state. And maybe that can force them to learn more complex dependency than just one hop or like recent behaviors. That might help boost performance. But I'm not sure how to do it like in a temporal graphs case where the graph structure is discrete and so on, but the timestamps are continuous.
mhm.
I feel like it might be a dynamical system problem. I was always intrigued by the connection there. Um,
Right, yeah, that's
your
a
thoughts?
very good point. Yeah, I feel like for most of the predictions we made so far is indeed just a forward way. And this work is just want to see if we want to enforce time reversal symmetry, the forward and backward way should align with each other. But in general, I think by forcing the reverse trajectories, we can also force the model to learn something different. Make a comparison. It's similar to like the masking thing used in LLM. So we have causal mask, which is just whether it's bidirectional or just unidirectional. And there's some recent work trying to revise something like usually in LLM will just make next token predictions starting from token t to make predictions to t plus one. But there are some recent studies saying that in order to for the model to fully comprehend the whole sentence, it
Yeah.
also helps to start from the last word to predictions on the t minus one word, so it can have a kind of a more comprehensive understanding of a whole sequence. So I think it's similar to temporal graph, but temporal graph is more like complex because we are not dealing with just a sequence. We are dealing with dynamic graph structures. So maybe there should be some more complex considerations here, but I think the intuition may share some similarity here.
hmm But I guess in a more general sense, so doing both forward and reversal are both like very interesting and starting points. But I feel like a more general thing would be if the model, so let's say the model is somewhat agnostic to the process, I take some input of any point in the process, it should be
Right.
able to go either forward or backward if it learns the dynamic correctly, right? So it might not be, let's say you want to go through the entire trajectory, but just say you randomly sample points along the trajectory and you ask the model to keep going forward or keep going backward. Um, in general, it should be able to do that. But yeah, just some thoughts as well.
Yeah.
Um, yeah, so if there's any question, feel free to type. Um, and yeah,
I
so
have,
yeah, go ahead. Yeah, go ahead,
yeah.
Victor.
So I have a question, and I thought it was really interesting. Great presentation. I think your slide on 9 out of 10 supercomputers in the world are being used for simulations. That was a bit surprising to me. So have you had any thoughts on like you talk about your models being surrogate neural models that could maybe replace some of these big simulations? Have you had any results in that regard on how they're doing compared to the state-of-the-art simulations, or if they're much faster to run or something like that?
Yeah, thanks for the question. I think the recent advance for neural simulators, I can consider it in two ways. I have some projects or I know some very good work that trying to use neural networks to accelerate the simulation procedure because we can always train ANs on much greater GPUs or TPUs. They can handle large amount of data. And for traditional numerical simulators, they will need to exactly solve each step by step, and the step size is usually very limited. So in this case, many neural simulators total goal is to accelerate the simulation process. And I think another line of work is what I have also previously mentioned. There are also many systems that we do not know the equation yet. We're trying to understand what's a hidden symbolic equation after that. So I think there are also some work in the line of symbolic reasoning for those systems, saying that they can one string, for example, a GNN, and then they can do symbolic regression so that they can extract the exact formula describing the system. I think previously there's an iClear paper trying to discover the formula behind black hole, and then they found that formula and then asked some like physicians, scientists to examine if those equations works or not, and indeed it gets verified. So I think like for those kind of work, it's more like new knowledge discovery. But still, I think there's also many painful point for neural network because it's solely trained on data. So there's many constraints it may not satisfy. And sometimes when you're making long range predictions, even though I claim my current approach is much better for long range compared to discrete GNNs, but the accuracies compared to traditional neural simulators, especially on the long range, sometimes is still not satisfactory. So it's kind of like a trade-off. So depending on what you want to achieve ultimately, but I think to totally replace traditional simulators, still a long way to go. Yeah.
Okay, cool. Thank you.
Yeah. Thanks for your question.
Yeah. Yeah. Thanks. Yeah. Super interesting discussion. And I feel like recently I've been seeing a lot of problems so similar to what you are talking about, but more like in the graph discovery. So let's say you have a bunch of time series that you observe and you want to discover the correlation, which can be represented as a graph, for example. There's a lot of these problems in practice, but I think the overall like this causal discovery of the underlying structure is a very hard problem, and there's very little approach so far. So
Right. I think causal inference itself is still like very like not totally solved, especially the causal discovery part is even more challenging compared to if we know the covariance, how we can model the effects of covariance directly. If we want to first discover what is causal relationship first, that is even more complex. So here, I think we just do some early exploration towards combining dynamical system with causal inference. But I think there's a lot of recent good work happily on the causal inference community themselves and also on temporal modeling themselves. So maybe we can try to track some of those recent work and think about how we can further improve our problem setting, modeling part, etc. But I agree, like causal inference itself, it's very like complicated alone, I think. Yeah.
yeah. Yes, for sure. Yeah. Thanks for the discussion, and then yeah, hope to connect at the future conference as well. And yeah, thanks for joining the talk today, everyone. And yeah, have a good rest of the week. And best of luck with Europe's rebuttals. And
Yeah, thank you everyone. And yeah, we can connect offline sometime if everyone's interested in chatting. And thanks everyone again. Have a good weekend soon.
thank you. Have a nice one.
Thank you.
Bye.
Bye,
Thank
guys.
you.
Bye.
Bye.